this XQ is being passed in here as an input, and then being passed through, and the software is nice. It shows you what value is on any given wire. So we see that we have that 1 and 1 coming through here, and they're becoming the inputs to this AND gate. 1 and 1 equals a 1. Good. It's working right. And then we can send that through to an OR gate. We can even connect it with this one. So we could say if 1 and not X or 1 and X, we get some value. And since at least one of them is a 1, we see that L changes. So I'm going to go ahead and connect L to this LED for a second. And let's just see what's happening. So I clock it, K changed, right? So K became a 1, which is going to be the new value going into our flip-flop. And our state is 0. If I clock it again, it goes to 1. Is L changing at the same time? If I hit clock? Nope. L is not changing. So our logic right now is set up so that L will always be a 1. So, if we wanted to, we could sit here for 2 or 3 hours and just check every box, try and get every single combination to create a sequence that we wanted to see. Like, say, both LEDs on, then only one of them on, and then both off. You know, just counting down. 2, 1, go. But we don't want to be here for 3 hours. We want to be here for 30 minutes. So what we're going to do is we're going to learn how to use Boolean algebra to just tell us how we want to connect it. And the way we're going to do that is with a truth table. All right? So first off, we have X and Z from our flip-flops. This is for our current state. So, what are all the states that we can see?
0, 0.
0, 0.
0, 1.
0, 1.
1, 0.
Okay, I heard 2. There's.
Well, it depends. Are you going to have one of the LED? Are you going to have both LEDs be on with the other off, or is it going to be the two?
We don't care about the LEDs right now. We just want to know what are all the states that our flip-flops, our memory, can be in.
Okay. 1, 0.
So 1, 0,
1,
1, 1. Does everyone see how that creates our states? Can everyone see how those are all the combinations? Okay. So now that we know how the memory can be, we want to know how we want it to change, right? So we have state 1, state 2, state 3. We can go to state 4 if we want. We can create some combination of LEDs, like red and green are on. Now only red is on. None of them are on. And then both of them are on again. We can, pick some combination however we want it. But we need to know how are we going to pass through these. And the way we need to do that is we need to know how are each of those flip-flops changing. How those flip-flops need to know when do I toggle to my other state value. So we can actually write an equation that will represent it as soon as we have decided how we want it to go. We want to go state 1, 2, 3, 4. We could also go 1, 3, 2, 4, 1, 4, 3, 2. You can put it in any kind of grouping you want. It's still 4 states. So let's go ahead and pick what do we want our new states to be. So if we're in 0, 0, we'll go ahead and use that as our starting one. Which state do we want to go to next?
0,
0, 1? Keep it simple. All right? Then what? We're at 0, 1.
1, 0.
Sorry?
1, 0.
1, 0.
1, 1.
1, 1.
0, 0.
0, 0. All right. So now we have a cycling deal. So we're just going to follow our pattern. 1, 2, 3, 4. Sounds good. And we're going to label these our next X value and our next Z value. All right? Now, the X and the Z flip-flops, you'll want them to change at the same time, but do they change? I don't want to phrase this question. does x care if z is changing or not?
Not here.
No, it does not care. So when we get its equation, when we figure out how it's changing, we get to ignore this nz column. We don't care what z is doing. We only care about x right now. And specifically, we care about when is x going to become a 1. Some beautiful magic in this. Once we have our Boolean expression or our equation, it will only become a 1 when all our requirements are met. If any of the requirements fail, it'll go to a 0 automatically for it. So we can really just pick one or the other to say this is what we wanted to do when we wanted to make a change. In our case, we like to pick the ones because that's what we're getting a signal from. Those are the cases we care about. So let's write an equation for our next x state. Any guesses on how that sets up? So I remember Roper mentioning it in class, the second hour from 2 to 3. Any ideas on how we're going to make this equation?
It looks like you just say, okay, whenever nx is 1, then obviously that means that the previous state has to fulfill it. So I'm going on a limb here. I would say nx equals not xz or x not z.
What was the second one?
X not z.
Okay. As it happens, he's right. We take our state that we're in, so we know that this state, our 0, 1, is going to result in a 1. So we need a term of our equation, a logic expression that says when we don't have an x, no x, and we have a z, then that needs to be a 1. So not x and z will equal a 1. And then we have another case. If x and not z, then we get a 1. So that's how we get these two expressions. Anding across the row, anding across the row, and then we use an or expression down the column. This or that will result in a 1. Anything else is a 0. And so that got us that expression. So we have an expression for nx. Let's make one for nz.
The first part would probably be not x and not z. That would be 1.
Not z. Okay.
Or x and not z.
Or x and not z. Can everyone see how we got that? So I realize I'm getting closer and closer to the whiteboard. Can you guys see the equations I'm writing? Are you good? All right. So that should cycle us through those 4 states. Let's see if it works. So if we come down here, let me go ahead and get rid of all these check marks. So here's our z. We're going to go ahead and give it a clock so that it can alternate. And we will set it up to L, right? Because we're going to have a different equation for the x than we can for the z. And we'll go ahead and put z in here. So we're looking at x. Let's read off its equation again. Read that off for me, please. Someone?
Not x.
So we have not x, right?
And
So
z.
and z. So we'll pass z just straight through, will not be x, and those two are now going to get anded. And then what else do we have?
X and not z.
We have an x right there, getting through, and not a z right there. All right. And then those two are also going to get anded, and then we're going to OR both terms, right? So the results of both those andings are going to get ORed through k. And that result gets sent back in here. So now, what about z? What does the z equation look like?
Not x
not X. They are not X, and not Z. All right, we'll send that one to the L. And what's the last one?
X and not Z.
All right, thank you. X and not Z.
Why'd you put it on G?
Because it wasn't looking close enough. And that one's going to get ORed with E, right? So E and F results are getting ORed, and C and D results are getting ORed. So now we have K and L should be the new values for X and Z respectively. And we've hooked them up, so let's see if it worked. Our current state is 0, 0. So what should the next state look like?
0, 1.
See if we're in 0, 0, then it should be 1, or you're right, 0, 1. Nope. No, we sent it to, yes, you're right, 0, 1. I can't read. All right, so we have 0 and 1. That looks good. Next one was 1, 0, right? That looks good too. And finally, 1, 1. And then we cycle back to 0, 0. Is that making sense to everyone? Everyone feel pretty confident about this? Good. Question?
I'm wondering how you knew to plug in the K and the L to the beginning of X and Z.
Because it's the ors. You want to match those, the ors
Right.
to the slaves.
So we set it up. We took our nx equation, the next x, so the value that should end up at x, which means it has to pass through w technically, right? So we said that logic is defined by taking our not x and z and ORing it with x and not z. So we checked out those, did the nodding and passing through, we ANDed it and got some result for 2 cases. We ORed it together, and then all of that is coming out of k. So k is spitting out our nx value. So now we just need to send it. Where does nx need to go? It needs to be sent to the input of our x flip-flop so that it can be the next state. Because we can think of it as a black box, but remember, it is a flip-flop. So anything that is put in here will get loaded in on a clock. So k right now is a 0, which we see right there. So our next state is going to be a 0. When we clock it, we're still a 0. But our input is now changed because this logic says, oh, when I'm in 0 and getting a 1 from z, that means that my next x needs to be a 1. Z will figure itself out. Someone else is taking care of z. But I know that x needs to change to a 1. So I now have it ready so that on the next clock, it can go to that 1.
Okay.
Now, you guys notice I used 4 AND gates here, but D and F are identical, right? So if you want to, you can actually combine them and just not even use F, and it'll still run just like it should. So there are 8 of them. You have enough to create as many as you will need, but if you want to double them up to save space, go right ahead. Question?
Do you just hook up XQ and ZQ to the LEDs? Or?
We're going to get there in just a second.
Okay.
So we talked about you can choose what state you go into next.
Mm-hmm.
So it kind of makes sense of it from 0, 0 to 0, 1. But how do you get the same equation if you go from 0, 0 and then you choose the next state to be 1, 1? I'm a little confused on that part.
So if we had a 0, 0, and then we wanted to go to 1, 1, then 0, 1, then 1, 0,
Yeah.
like this. The answer is the equation would not be the same. We would get a different equation because we're cycling through the states in a different order. And so to do that, we would need a different expression. Now, it would still be a 4-state machine. So just because we went from 1 to 4 to 2 to 3, and then back to 1, just because we're changing the order doesn't change the fact that we have 4 separate states. Now, if we had it hooked up to the LEDs, like what he suggested, if we hooked the flip-flops directly to the LEDs, that would change what the LED output would look like, because then the order would matter. This is why we're not going to connect it directly to the flip-flops. We could, but then the order that we go through the states becomes important. We're going to do it in a way that's just as easy, but the states won't matter. It'll just know how to say, when I'm in this state, I will do this. The order of the states is less important.
So could you still cycle through with one equation? Because I noticed that we didn't have to write out every single state of, the next state of x, because we had one equation that would cycle through it. But is that going to be true with other patterns? Does that make sense?
I want to say yes, but I don't fully understand the question.
Well, nx and nz, we can calculate from x and z.
Right.
And then the next one after nx and nz, we know that that equation will still work for them, right?
So you're saying another equation, like if we added a next q right here?
No, if you had like an nx and nx, like the third one. So when it starts with 1, 0, and then goes to...
Like another variable here?
Yeah. I'll talk to you after about it, because I might be the one with this question.
Well, probably not. So you're saying, like, what if we had 3 variables?
No, I'm saying that we have state number 1, which is x and z, and then
Right.
we have the second state, which is nx and nz. But what about the third and fourth state? We didn't
Okay,
draw
so this isn't the next state. So these are all our states. So we just have 4 states, and then this is just where are we going to go. So we go to 0, 1. So if this is where we are, we'll go here. We'll go down a row. We could set it up like this, where we went from 0 to 0, 1, to 1, 1, to 1, 0, to 0, 0. So this is the state we're in. We go to 0, 1. So we go there. Okay, this is the state we're now in. Then we say, okay, what's my next state? 1, 1. So we're going to jump all the way down to here. And then we say, okay, what's my next state? 0, 0. Okay, I'm going to jump back here. 1, 1 to here, to here. So you'll notice we actually, because this state only goes to itself and nothing else gets there, we've created a 3-state machine. We just ignore this middle state. Does that answer your question?
I think so, yeah.
Okay.
So you can determine the order you want it to go, as long as you have an equation to.
Yep. And that's how you can also create a 3-state machine, or if you had more variables, a 5 or 10-state machine, or anything in between. As long as you have enough variables to represent it, you can just define how you get from state 1 to state 2 to state 3 to state 10. And then look at your outputs and say, okay, here's the equation that expresses how each variable kind of alternates through its different sets of states.
Thank you.
Okay, but what you might also have been thinking of, as TAs, we usually extend this, because there are actually 2 more things we care about, and that's the LEDs. LED red and LED green. We can also define how we want them to change as we go through this. So if I jump back to our original 0, 1, 1, 0, 1, 1, 0, 0, right? Because that's the expressions we're using. Let's say we want these LEDs to do something while we're at it. Let's go ahead and say, how does both of them on, then only the green one on, then both off, then both on again. So kind of a 3, 2, 1, go. Doing a little race here. Any guesses on how we can get those to function? I'll give you a hint. It looks a lot like something you've already done.
When you just try to match the states of the lights with the states of the NX and the NZ, or maybe the X and the Z.
So we want to match.
Oh, never mind,
these
never
to
mind,
this,
sorry,
or-
no, never mind. So what you're saying right here is that when what we're assuming here is when X and Z are 0, and next state X is 0, and NZ is 1, then the lights will be 1 and 1, correct?
Mhm.
Okay.
So this is saying our state, this is what the state looks like, this is what the LEDs look like. This is just what they should be doing. This is the state, this is what the LEDs should be doing, so on and so forth. So the LEDs are not a next state. They're going to happen right away. But will that affect the logic on how they figure that out? No. It's a it turns out we can write an equation for the LEDs the exact same way we wrote equations for the next state. So we can do an LED red and get an expression for it. So now we're looking at this column. Sorry?
So the first one would be not x, not z.
So not x and not z. Good. So that takes care of this one.
Plus x, z.
Plus x and z. Or x and z. Does everyone agree with that? You all okay with that? All right. And then let's do the green LED real quick.
Not x, z.
A little louder, please.
Not x, z.
Not x, z.
Or x, z.
X and z. Is that it?
Or not x, not z.
Or not x, not z. Good catch. So in this case, we have 3 ones on our LED. So it's going to have 3 terms. All right. So there's our new expressions for the LEDs. Beautiful. And quite conveniently, we have 2 more gates up here, N and M, that aren't being used yet. So let's go ahead and set these up to our LEDs. We'll go ahead and make the red one M and the green one N. So, starting with M, our red LED, what logic do we need?
Not x, not z.
So not X and not Z. We use that one yet?
Yeah,
E. So not X and not Z. So we can send that one to M. And look at that. It turns right on. Because we're in the 0, 0 state. So it just knows, oh, hey, look, red, I'm supposed to be on. And what else? Is that it?
x and z.
We need X and Z. So that's going to be this one and this one. So we don't have that one yet, do we? So we'll connect that one to M. Oops, not to M. Where am I going? We are connecting this to M. X and Z, is that right? Yeah. No.
Yep.
Yes, it is. I looked at the wrong one. Okay. So now if we go through all 4 states, very good. So the red LED is doing as we want it to. How about green?
So not X and Z.
So not X and Z, which I think we had already.
So
Not
we have that, we just added the N.
So that one will go to N, not X and Z. And what else?
Z, X and Z.
So X and Z, which is right here. That one can go to N,
Not X, not Z.
not X, not Z.
So E.
That one already up there? Not X, yep, not Z. All right, so we're in our 0, 0 state. The LEDs look like they're doing what we want. So 3, 2, 1, go. And we go back to 0 and they stay on. And would you look at that? We can now run it. And it just goes. Beautiful automation. The glory of computers, right? And that's all a finite state machine really is. It's just giving a computer just a process to run through. In this case, we created an infinite loop so we can just run forever. That's all a stoplight when you're driving is. Red light, yellow light, green light. 3 states. And you'll get to actually see that later. We're gonna program a stoplight in lab 5. We get to do it in assembly. But that's really all it is, state machine. Any other questions about the lab? You guys feel pretty confident you can do it?
So this entire time it's just going to be dealing with 4 states, the entire duration of this lab?
No.
Okay.
There will be 5 different parts that'll all look like this. You will want to create a truth table for it, and then the LEDs will just map out in a different way. One of them is counting 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 2, 3. Another one is like a lead follow, so on, off, on, off. Just stuff like that.
So a few of them aren't going to have more than 4 states?
Yeah,
Well,
one of
each
them is going to be a
goes-
3-state machine.
Okay.
One of them will be a 3-state machine.
Okay.
And suggesting there's a little save button down here. Save each one that you do, and it'll just save a text file that you can load later, and it'll just remember where you put all your check marks. So you can go through all the different ones. When you're ready to pass off, you'll just say, okay, I will load, here's requirement 1, here's requirement 2, requirement 3. We'll just go through all 5, we'll see that they all work right, we'll look that you did the truth tables. It's been a half hour, you go home.
So we don't submit anything online, we're just showing what you guys did.
No. There will be web submission for like your points, but there isn't any code or anything that you need to submit. Just show us that it's all working. Yep. All right.
And we're just showing you on this, right?
Yeah.
We're not getting into the CSS or anything, or
No,
CCS.
no, we won't be using Code Composer for this. Also, a little hint: there is an extra credit option aside from doing it early. It is extremely easy. Look at it, read it, and you'll realize it is like, if this already isn't easy enough, the last extra credit is really, really easy. Go ahead and just do that, and it'll take you like an extra 30 seconds. And it's a whole extra credit point, so totally worth it. All right? Okay. That is everything on the lab. If anyone has questions on homework, feel free to stick around. Otherwise, you're free to move on with your lives.
Let's bring the pass off. You're on the